Hello everyone. Thank you for joining us for today's Deeper Talk seminar. My name is Jarrett Heiss. I'm the Science Director at SURF. Before introducing our seminar speaker, a few housekeeping announcements. Today's event is in person as well as online. Questions will be answered at the end of the presentation. Those in the room can raise their hand, and those on Zoom can also do the same. We'll unmute you so you can ask your question. Along with all previous Deeper Talk seminar presentations, this talk will be recorded and available to view online at institute.surf/deeper-talks, as well as on our YouTube and Vimeo channels. If you wish to receive notification for upcoming monthly talks, go to the Connect link at the top of the Institute webpage. Now it's my privilege to introduce today's speaker. Shortly after graduating with a PhD in nuclear physics from MIT, Dr. Jose Alonso joined Lawrence Berkeley National Laboratory in the early 1970s and was part of Glenn Seaborg's team that discovered element number 106, seaborgium. In the accelerator division at Berkeley during the 1980s, Dr. Alonso directed operations of the lab's world-leading accelerators, pioneering new fields in relativistic heavy ion nuclear physics and cancer treatments with accelerator beams, topics he remains passionate about today. After retiring from LBNL in 2002, Dr. Alonso landed at SURF in 2007 as the first laboratory director, reopening the Homestake gold mine and preparing the 4850-foot level for science. Jose's vision for science at SURF was pivotal. It's no exaggeration to say that we would not be here today without his early leadership, for which I, for one, am very thankful. Since his time at SURF, Dr. Alonso has returned to accelerators and a new generation of high-powered cyclotrons with applications to neutrino physics, a future version of which may find its way to SURF. Let's get set to learn about a path from Homestake to SURF, the early days, and thinking beyond Dune. Jose Alonso.
Thank you, Jared. I'm live here, and I'm glad to see you and all of you online. I'm going to talk to you about the early days and the adventures that we had in reopening the mine and bringing science underground here. But also I'd like to conclude with some thoughts about where we are today and maybe visions of where the laboratory will go in the future. So as Jarrett said, I was the first lab director in 2007, 2009, but I've remained very closely connected with and follow the progress very, very keenly. And but I also have positions at MIT and at Lawrence Berkeley Lab. So let me see. So the early days, the birth of Dussel, now SURF. In 2002, Homestake announced that it was going to close. And Homestake had a long legacy of science with the work of Ray Davis and the first detection of solar neutrinos. And this was in the 1960s, and he had developed a large group and a large family of scientists who were keenly involved with the underground work. And so when Homestake announced that they were going to close, this group got together and said, this is the perfect opportunity, and went to Barrick and said, look, if you can donate this to the National Science Foundation, or essentially have it dedicated to science, this will be a huge benefit. And Barrick Gold were actually very, very supportive of this. And they said, however, there's one thing that you must do, and that is that we insist that you carry a liability insurance policy to protect us from anything that any dumb scientist is going to do underground. As they knew, scientists in general don't know just how hazardous the environment underground is. So this is a very, very reasonable request. And so the National Science Foundation, presented with the prospect of having this, have this donation, they defined a very lengthy process that essentially started with, is there a need for an underground laboratory? There are some around the world. Why do you need one here? So that took a year. And Bernard Satellet at Berkeley did a very extensive study on this, and the answer was yes, yes, yes. There's as much underground space as you can have is going to be used. So the next National Science Foundation said, fine, okay, is there anybody who'd be interested in hosting this? And so around the whole North American continent, there were 8 responders. And so they then defined a very lengthy process of down selecting. And however, the question, we said, insurance? He says, no way, I'm sorry, you know, we can't use taxpayer money for buying insurance policies. Well, they sort of buried that under the carpet. So anyway, this process was taking so long that Barrick eventually got tired and they shut the pumps off. And as the inflow was 700 gallons a minute had been measured, this was a real issue. But in the meantime, Kevin Lesko at Berkeley sort of marshaled the forces and started working on Homestake. So meanwhile, in South Dakota, governors, first Bill Janklow and then Mike Rounds, said, look, this is a marvelous opportunity. Yes, we must take care of it. And yes, Homestake is obviously the place where this has to go. So they started fundraising. $40 million from the legislature and $70 million from Denny Sanford. As far as the insurance question was concerned, Mike Rounds said, well, yes, I have the same problem. I can't use taxpayer money for that. But I can found a private public agency or association, which essentially the private arm of that can buy the insurance policy. So the National Science Foundation said, look, we've got our process set up here, and whatever South Dakota does with its money is their business. We don't care. Just as long as you do not interfere with our process. So there was a firewall. They said you have to have a firewall built between NSF and what South Dakota decides to do with its own money. So Mike Rounds said, fine, okay, let's go. Let's start this process going. So a contract was awarded to Dynatech, a mine services company, to reopen and get things going, and which was overseen by the South Dakota Engineering Office in Pierre. And so they started recommissioning the hoist equipment, which Barrick had done a very good job of mothballing. And so that was really perfect. It was very easy to bring those back up. And however, when they removed the covers from the shafts, the corrosion that they found in the Ross area, which is a steel frame, was extremely severe. And this was a real problem. Okay, so anyway, that was the start of it. Anyway, the down select process sort of marched along, and finally in July of 2007, the announcement was that yes, Homestake was selected as the site. But DOE said, look, we selected the site, now you've got to essentially do the proposal for a laboratory. So Kevin Lesko and his group at Berkeley put together a DUSEL team, Deep Underground Science and Engineering Laboratory, and started working. But meanwhile, what was happening in South Dakota, which is again sort of independent of this, was that things started. And so I was recruited in October of 2007, and the main credentials that I had, first of all, experience with this kind of project. So I've done some of these. But the most important one was that because I was long retired now from Lawrence Berkeley Lab, I had no official connection with NSF or with DOE. So I was a private citizen. So I'm on the right side of NSF's firewall. And so I came and I talked with Pat LeBrun very briefly, who is one of the key members of the SDSTA board. And within about 10 minutes, I was basically said, come on board. And so I became employee number 6. And I don't know what, so Greg, you were number 2 or number 3 or something like that. So anyway, so the leadership, the team that was there basically was Dave Snyder, who was the executive director of the SDSTA, and his right-hand person, executive administrator, was Trudy Severson, and working also with Dave Bozade, who was the chairman of the board of the SDSTA, and Greg King, who was right here. And Greg brought the mining. Nobody else knew anything about mines. And Greg was the guy who had the experience and who knew the underground environment and knew the people. And the people who had worked for Homestake with a tremendous numbers of years of experience. And so basically being able to get things going was really a credit to Greg. And so thank you for that, very much so. But anyway, here we are. So drivers, so we had to start your engines. And so the tasks that we had to face were, first of all, where's the water? And pump it out. Second is, if the water is above, especially if it's above the 4850, we had no idea where the water was. Because the shaft was, we could not go down until the shaft was rehabbed to the point where it was safe to go down. But then the second one was, once we get to the 4850, open it up and recondition it, refurbish everything, and then get science going. Those were the missions that this is what I had to do. So the first is, where's the water? So Homestake had put sensors at the 8,000 every 150 feet up to detect the presence of water. And slowly, after they turned the pumps off, one by one, these ticked off. Tick every couple of months, another level would be flooded. And Dynatech's comment was, look, this is dangerous. It's not safe. And that is one of the key. Okay, one of the those it's not safe are that's the killer phrase. You can't. So anyway, so I said, well, what will it take? And so their response was, about 3 years and $100 million. We got to rebuild the entire thing. So, well, I want to get science going here and we get down there. So this was not something that we could really afford to do. So. Dave Snyder said, look, the governor has told us that we can use any resources in the state that we need to get this going. And so Dave said, there's this particularly really sharp engineer in the Rapid City State Highway Office, whose name is Todd Seaman. And he says, why don't we try to bring him on board? So I called Todd, and he was willing to do that. And so he came up, and he didn't know anything about mines. Or underground, but by golly, he knew contracts and he knew how to deal with contractors, being in the highway department. So his response then to Dynatech was, okay, if it's not safe, define safety. And so, fine, this is an engineering question that has an engineering answer. And so they went back and they calculated, and they said, okay, we define safety as you have a fully loaded cage, and we have a cage right back there, a fully loaded cage that is traveling at maximum velocity, about 30 miles an hour, and it goes into free fall. Something happens with the equipment or whatever, and so now you have this thing that is plummeting down. You have so that there's structures that you can actually see in the cage back there, which are there are clamps that when the cage goes into free fall, spring tension is released from the rope and from the cable that's holding it up, and these clamps then engage into a wooden beam that is going the full length, and so it could be anywhere. And so this clamping in here slows it down, and it has to slow it down. The definition of their definition of safety was within 3 sets, which is 18 feet, and the shaft cannot collapse. So if the corrosion is such that the steel is just really weak, then in fact those elements have to be rebuilt. And so what they calculated was that the normal beams were 3/8 of an inch angle iron, I-beams, and if there were 3/16 of an inch, there would still be enough strength to be able to do this. So okay, so that was then it meant that we didn't have to rebuild the entire thing. We just had to go down and inspect every one of these things and replace only the ones that were necessary for this. And they had the momentum and the force and the stresses all calculated to which ones were the really critical ones that had to be looked at. But so with this solution then, we were able to make rapid progress down in weeks and not in years. And so this was an amazing thing. So finally, yes, we did get down to the point where on May 5th of 2008, the water was found. and it was at the 4660, so that the 4850 was already 200 feet underwater. So that was, but that's the information that we needed. It says, but we had some real problems, which was that particular winter and spring was very, very wet. And so we were able to start tracking the water because we knew where it was, and lo and behold, it just kept going up at a very rapid rate. And so we had to deal with get the pumps going. So the pumping infrastructure in the Ross shaft, there are a number of pumping stations every 1,200 feet or so, 1,250 feet. There's a series of pumps, and there's a reservoir, and the pumps pump from that reservoir up 1,250 feet to the next reservoir, so that they were sort of in stages then where you could have the water coming up. However, when we got to the first level, the 1250, as expected, because the environment is hot, 100% humidity and very, very hot, the motors needed to be replaced, the pumps all needed to be rebuilt, and the electrical system, all the electrical cables had to be redone. So that was a massive undertaking. However, this was done in record time. And I think this is me and it's funny. One of my old friends from Berkeley said, who was an experienced geologist, he said, Jose, there's something really wrong with those pictures, and that is that your coveralls are far too clean. You don't look like a miner. He says, give me those coveralls, I'll make you look like a miner. But anyway, this is probably one of the highlights of my time here. And so in March, this was the date of these was March of 2008. So this was a few months before we'd actually seen the water, but nonetheless, it was the beginning of things. And so we made rapid progress with the pumping. They say the 1250 was ready in March, the 2450 in April, the 3650 in May. And between April and May, that's when we actually found where the water was, so that this work was actually going along. But then a series of submersible pumps, which were shown here, were put in to be able to get from the water up to the first large station. But all the pumps were finally turned on in June 9th of 2008. So this was the time. However, you see that the water level is still going up. So it took a long time and a lot of patience to essentially get the pumps to go to where we started actually going down. But then, so in December of 2008, we were at the point where we could essentially say, okay, we can now predict how long it's going to take us to get to the 4850. And so these were the predictions, and it was going to take a number of months. And the actuality was that yes, we actually reached it in April of 2009. And you can see that once we actually got down to the top of the 4850, the volume was so huge that it took a long time to pump all the water out of that particular level. But a lot of wonderful things happened on the way down as we were sort of reopening this. And so one was over here was Tom Reagan, who was right here, who had been instrumental in the closing of a lot of these levels when Homestake was leaving. And so now he's going to the same signs that he said, here is the closure, and this is the day which is reopened. And the captions were basically, Tom is back. So, but the other thing which was wonderful was that you can see this picture over here. It says, I'm home. And the first cage that went down the 4850, the temperature is 90 degrees, about 35 degrees centigrade. Humidity is 100%. It's mucky, wet. You can see but in fact, the first cage, the miner opens the cage up and he jumps out into this environment and says, I'm home, I'm home. And that was just wonderful. This picture on the left over here, on the right, is interesting. This is a picture looking up at the ceiling, because in fact you have structures where in fact you have air bubbles that there's no way for the air to escape, and so the white is an air bubble, And because it was not exposed to the water, but the brown around it was exposed to water. And so you can sort of get a hint as to what the water was like. Because now the question is, okay, what do we do with this water? Now we have a way of getting it out. And so when with Larry Stettler, who was one of the School of Mines hydrologists, and his graduate student, they came and did some water sampling. And I remember we all went down. It was about 6 o'clock in the morning, and then down on the platform, down to the point where we could actually get the 1,000 feet or so from where the water was to be able to pump it up. And the water came out first, as you can see on the left, very, very clear. However, within a minute, it was brown, completely brown. And so what was happening was that you have a state of iron, an oxidation state of iron, 2+, which is converted to insoluble 3+. And so that you were getting this precipitate of iron, which you can see on the right over here is this ugly mess coming out. And so, there's no way that this water can be released. How was this handled? Well, there was an ingenious win-win solution that was worked out with Barrick. And on our side, I think it was John Sheets that was the instigator of this, and then on the Barrick side, it was Todd Dix. And I'll go through this quickly over here. This is a surface map of the property donation, and you can see it includes the areas of the shaft of the Yates and the Ross, but also up in the top corner there's a water treatment plant. So we had the water treatment plant from Homestake. So this is part of it. The second part of it, and this is an overlay over here, there was a large lake, which was what we call the impoundment dam, now it's called the reservoir, which was where water from the processing of the gold that Homestake pumped into this lake. And it contained trace amounts of cyanide and ammonia, which were used as part of the gold extraction process. And there was an issue over here. This was a Superfund site, I believe it was, because this is just contaminated area. So the solution was to put in a transfer line to pump the water, or if it's higher, so it actually just let gravity feed down from that lake down to our water treatment plant. And so here are reservoirs, and you can see the mine water on the left, which is brown, but the water coming from the impoundment dam was clear. And so we had hot temperature. Their temperature was cold, because this was now, after so many years, it's only runoff. We had huge amounts of total dissolved solids. They had essentially none, because this is now mainly snow melt and runoff. And so the idea then was to combine these, bring these two streams into the water treatment plant. We had sand filters to take care of our iron, and every once in a while these were flushed, and the amount of iron that came out of our water was like 2 tons a day. So actually there was a professor from the School of Mines that came and gathered several of these barrels of iron oxide, and with his students made samurai swords. Went through the whole process of making samurai swords with this. The Homestake had these biological processors that were used for cleaning the water, cleaning the organic material, the cyanide and the ammonia from the water. So that's the way that was processed, and then the water was combined and came out as a waterfall. And this is a picture that Bill Harlan, who was our PR guy, took. He was just sort of driving by, and there was this biker that was standing there admiring the waterfall. He says, "I just love waterfalls." And so this is we're environmentally going well. Okay, so we've got the water done. So the next is we can now get down to the 4850. So that the 4850, the refurbishment of that started as soon as we possibly could, and it involved we were going to take care of the Davis area and reset that for new experiments. So it was taking the old tank out and rehabbing the drifts and setting up surface facilities for the experimenters. So these are pictures of the Davis cavern being, and it was enlarged and set up. And actually, before this was done, we actually did have a dedication at what's now known as Governor's Corner. And this is Denny Sanford and Mike Rounds with a plaque, which I just saw a couple of days ago, down in this area of the place called Governor's Corner. And so this was the official opening of the 4850. Okay, so there we are there. Now, this is not chronological because, in fact, science startup actually occurred in parallel and a lot earlier. So what we did was we had our first users meeting that was scheduled in April of 2008. So mind you, this is a couple of months before we even knew where the water was. So we set out an announcement, we expected maybe 200 people to come. The total number that came was 375. So this was, this is a message that, yeah, you don't know where the water is yet, but this is going to be a successful laboratory. So that was a wonderful vote of confidence. And so in that meeting, I put together a program advisory committee, and we looked at 37 different proposals, and in physics, geology, geophysics and biology, microbiology. And shortly thereafter, we brought Jared on board. And so so Jared has been really here from the very start. So the early science over here, as I said, and this did not require the 4850. These were experiments and sort of investigations that could be done at the shallower levels that were accessible much before we actually had the 4850. And so the geology, Bill Rockentine was set up a series of seismometers, and at one point he came bounding into my office with these traces. You can't see them there, but I've blown this up over here, and you see these traces, and that's detection of the Fukushima earthquake, which occurred in 2011. That was picked up by our own seismometers right here, so that a lot of very, very successful early science done in that. And when the 4850 was set up, then we had two major physics experiments, which was LUX, and now the picture on the top left is the Davis Cavern after it was finished, and inside there is a picture of the LUX tank, which is this right here. This is the LUX tank, and that the large water enclosure that that person is standing in that tank was filled with water. And now it was big enough for the next generation, which is now in the process of just sort of wrapping up his data taking. But also the other major experiment was the Majorana demonstrator, which is a neutrinoless double beta decay experiment. And the key thing about that was that it needed ultra pure materials. And so that a system was set up for electroforming copper underground, because copper that's on the surface, cosmic rays hitting it produce a very small, but nonetheless very important radioactive component that is background for the experiments. And so that you have to totally remake the copper if you're going to use it for these experiments. And that is, the MJD is now finished, but that copper is being shipped all over the world to different laboratories. And it's really, I think it's just only a few days that it can be on the surface, exposed to cosmic rays before it, so it's very quick transportation back and forth. So anyway, there we are. Basically, we accomplished the tasks that I wanted that I was sort of charged with doing. And so the laboratory is launched. However, as we all know from history, it was still not a smooth road. Because again, there are two things going on. There's the NSF process, which is being handled in Berkeley, and this is the Dussel process. And then what we're doing over here on the other side of this famous firewall is funded by the state of South Dakota, and is South Dakota that is responsible for it all. Because what happened was in 2011, as we all know, the National Science Foundation canceled the Dussel project. And the process is also taking budgetary credit for this. And it was a time when the government spending was being looked at, and the National Science Foundation director in testimony to Congress says, well, I've done my part by canceling a $700 million project. And this was sort of specious because, in fact, no money had been appropriated for it. So he wasn't really saving the government anything because no money had been allocated to it. But nonetheless, it made him look good. Okay, so however, as I mentioned, because we're on the other side of the firewall, the fact that this is having a problem did not really affect us. And we always expected that that this would become part of the National Science Laboratory program, but in fact, the road to this is rocky and bumpy, as we see. However, SURF survived and is clearly thriving. There's no question about it. Because a huge amount of efforts went in then with Ron Wheeler and Mike Headley, and Casey Casey Peterson was the chair now of the board of the SDSTA on the South Dakota side, pressuring, and on the Berkeley side, Kevin Lesko and Paul Alivisatos, who was the laboratory director at the time, working with DOE. And it's always obvious that this should. The NSF was sort of a crazy way of thinking of. Normally you have large science experiments that may be funded by NSF, but they're performed at DOE laboratories. And here we were going to have Dune at an NSF, which is a DOE project, at an NSF laboratory, and that was sort of crazy. But so it always belonged in the DOE family, and this was. This is actually the way it came out. So at first, we emerged as a DOE laboratory, but under the Lawrence Berkeley Lab, so we're connected with LBL. And then when the Dune project came along a little more seriously, it became it was under Fermilab, and now it's autonomous, which is exactly really the place where it belongs and where everybody had hoped it would get to. So that's where we are. And as we know, the Dune project is working very nicely, and the caverns have been excavated. I had the honor of going down there on Monday, and the size of these things is just it's mind-boggling to consider how huge these caverns are compared to the spaces that we've been used to seeing. So this is going now very, very well. And I'm very, very pleased to do that. But the other thing that I'm really pleased about was getting information from Jared about expansion plans of beyond Dune, of new experimental spaces underground. And the fact that, so that you can see the blue things are the Dune caverns, but around close to the Ross shaft now, what is sort of shown in olive there, is now completed, which are sort of access ways. New drifts have been put in there, and with the idea of future building of these two other large caverns that will be approximately this, not as long, but roughly the same cross-section, the same area or the same cross-section area of the Dune caverns. So this is ongoing and really shows expansion capabilities, the approval for this. So that's end of the first part of my talk, and in the last 15 or 20 minutes that I have, I want to tell you sort of my vision for the future. I'm going to discuss two ideas, none of which have been endorsed yet by the SURF management, but our feeling is that if we can proceed along this path, it will really, really increase the capabilities of SURF. So the first is there's a new detector technology, a detector called Theia, which is a water-based liquid scintillator, and of which the scale of the detector is about the same scale as one of the LBNF detectors. But it's not liquid argon, and it's a totally different kind of way of collecting information and collecting and recording the events. And the proposer of this is a young lady, Gabrielle Oribigan, who is at Lawrence Berkeley Lab and also is a professor on campus. And so I'm going to talk a little bit about that. And this is Thea, and she is, the fact is that this is sort of a new development in detecting light, detecting events that is much more sensitive, but also because it's in the same neutrino beam from Fermilab, they can also do the same measurements that the LBNF detectors are doing in a complementary fashion. So it's a way of essentially gathering more information from that. But in fact, and technically, the scintillators typically produce, radiation comes in, a particle comes in, deposits energy, and a scintillator will just convert that energy into light, into photons, but they go all over in any direction. So you get a lot of information, but you don't get any information about the direction in which the particle came in. However, if you have a particle that's going faster than the speed of light in the medium, you have something called Cherenkov radiation. And Cherenkov radiation is very characteristic and really directional. So by being able to combine the information, so the water-based liquid scintillator, the water part of it gives you the Cherenkov radiation, and it also, Cherenkov radiation is a lot less, is a lot dimmer than normal scintillator light. So by having a water base in there, you can dilute the scintillator down to where the level of the signals can be comparable, so that the Cherenkov information is not lost. So you can get not only the energy information, but you can also get the directional information from this. And so this is a huge new development over here. The other thing about Cherenkov light and scintillator light is that the spectral, the photon spectra are different. So that there's a technique which was pioneered by Josh Klein at Penn, called a dichroicon. And so this is really interesting because you can have a particular kind of material that you have light striking it, and if the wavelength is low, it transmits. If the wavelength is higher, it reflects. So you can actually separate. I think I've got those right. They may be opposite, but anyway, you can separate the light into two different paths, and so you can then get more information out of this. And the scintillator light and Cherenkov light have different spectral characteristics. She is actually doing a small demonstrator called EOS at Berkeley right now, and they're testing out this dichroicon also. But a slide that she sent me, which is the reach of Thea in the dune beam. So it's complementary to the LBNF detectors, but then also it's extremely sensitive because of the characteristics of it to solar neutrinos, geoneutrinos, and the supernova. You heard a talk not too long ago about supernovas, and also, long-standing thing is the proton stable? Is there a way of getting, if proton is not stable, then eventually, and the lifetime for the proton now is something like 10 to the 20th times the life of the universe, but they're still looking for it. So there's a lot there. Now, Thea, there are several other around the world very large photon detectors. Based on scintillators or water. And so Thea compares favorably with all of these. The volume is roughly 20 kilotons of fiducial volume. Hyper-K, which is in Japan, is much bigger, but it's water only. So she is combining, and Juno is in China, is about the same size. Our depth is much higher, much greater than those, so the background levels are much lower. And she's getting neutrino source here, not only from the ground or everything, but also from dune. In Japan, it's T2K, and the Juno is getting reactor flux about 53 kilometers away. And so our baseline is 1,300 kilometers. So these are how they compare, and it's certainly, Thea is one of the, is a clear advance, stands out very, very nicely with the other ones. So it's something that's really worth doing. And my vision would be that in fact Theia would go into one of the new caverns that Jared is planning on building. So that's one of the ideas. The second idea is that we've got here, LBNF is getting its neutrinos from Fermilab. Japan is getting its neutrinos from T2K, which is another big accelerator that's 200 kilometers away, or reactors and whatnot. And so an idea that we've had actually started in 2010 was, why don't we bring the sources of neutrinos down to where the detectors are? And so that's what I'm going to talk about. And this was an idea that first Janet Conrad first had, and Mike Shavitz at Columbia, Janet's at MIT, in 2010. And we've been working on that ever since, basically. And sort of when I left here, I joined Janet's group, and I've been working with them. And so my field is accelerators, and so this is bringing accelerators down is really one of the things that I'm very keen on doing. So the thought that I have too is that in fact we build a new cavern. I'll go into the reasons why there will be a new cavern for these that is sort of more or less between the LBNF and the Theia detectors. Sort of in a space that is clean, there's nothing there now, and this is a tremendous advantage, as I'll get into. But what one would do, and the accelerators that we've been looking at are high current cyclotrons, and there are sort of a family of two of them. There's a smaller 60 MeV. These are all cyclotrons with beam currents of 10 milliamps. Now, this is a factor of 3 to 5 more beam current than anybody has ever seen out of a cyclotron. But we know how to do it, and we actually have been doing the development of it, and have good confidence that in fact we can reach this. And so the 60 MeV cyclotron produces a beam of 60 MeV protons that can be put into a target, and there's an experiment that we've been working on called ISODAR, which sort of uses this. But in addition, in the very early days, before Dune really came up, there were thoughts that in fact there would be like megatons worth of water detectors built here, and so we thought then. Water detectors are particularly good because there's something which is called inverse beta decay, which is very, very sensitive way, but you need water for that. Sensitive way of detecting neutrinos. Liquid argon, there's no inverse beta decay. So once the technology sort of shifted from water to liquid argon, then the idea for Daedalus sort of was put on hold. But nonetheless, building these large 800 MeV cyclotrons could actually produce a different kind of beam. And the kinds of, so basically the way in which we use the proton beams is for ISODAR, we run the 60 MeV protons into a beryllium target, which produces lots of neutrons. And the neutrons then flood out into a sleeve that has lithium-7 in it, which makes then lithium-8. And lithium-8 is a particularly good beta decay spectrum. The 800 MeV goes into a long graphite target, and basically it produces pions. So it's the decay of pi plus that we're looking at here. So that what these accelerators do is they give you, the low energy one gives you a very, very clean beta decay spectrum of neutrinos. So you can see it's an electron anti-neutrino flux, and the lithium-8 beta decay has a very high endpoint energy of about 14 MeV, which is very much above the normal background of neutrinos, and so that it's a very good, clean source. The 800 MeV is essentially a pion decay spectrum, and the pion decay spectrum, some things got lost over here. That's probably my fault over here. But a characteristic neutrino spectrum, which is a little higher energy, is about sort of between 30 and 50 MeV, but also very clean and very well understood. So now the thing that's really interesting about these is that if you look at the flux of neutrinos that you get from these targets, and these are done by simulations using a program called JAMP4, which is a very well-established and well-calibrated program, so we're quite confident in the results over here. But that what you have is, for the 60 MeV, for the lithium-8 spectrum, you have roughly 1.6% yield. What that means is that for every 100 protons coming in, or every 1,000 protons coming in, you get 16 lithium-8s, so that you have as generators of this. And for the 800 MeV, it's roughly a 17%. For every proton, you get 17.17 of pi pluses. So total fluxes then that you have are something like 10 to the 15th, because if we have, again, 10 milliamps of protons, 10 to the 15th total flux, or 10 to the 16th for the higher energy. Now, mind you, these are what are called decay at rest sources, so that in fact there's no directionality to them. They essentially are uniform over an entire 4 pi. But I want you to pay attention particularly to these numbers over here, because everything else is derived from that. But one point, many of the neutrino experiments are saying, or large detectors are saying, that it'd be nice to bring a radioactive source in, put a radioactive source very close to one of these detectors. But bringing a radioactive source in of the strength that's needed is all sorts of terrible problems. You got to make it, you got to transport it. Typically, these things also have half-lives so that they will decay over time. And the attempts that have been made to bring radioactive sources to Gran Sasso, for instance, have all basically failed. And now it's even worse because these sources all came from Russia. And it's almost impossible to get this done. But our our lithium-8 is essentially the equivalent of about a 27 kilocurie source of lithium-8. And this is about the strength of the sources that people are trying to get. But the advantage that we have is that you get this neutrino flux, but if you turn the beam off, the radioactivity goes away. And you don't have a half-life. This thing doesn't decay. It's strictly a function of the beam coming out of the cyclotron, which is not going to decay. So this is it's a very effective source. So if I now look, so if you consider you've got your source of neutrinos over here, and it's producing neutrinos over a sphere that's essentially 4 pi. If I ask the question, what is the flux density? Namely, if I go a certain distance out and look at how many neutrinos are going through this, that's a number that will drop by the square of the radius of the distance. So if I take a baseline of, say, so what I've said here is like 50 meters, for instance, over here, I still have like 3 million of the low energy neutrinos and 30 million of the neutrinos from the pion decay. This is at 50 meters, and this is neutrinos per centimeter squared per second. So if I compare that number with the flux that's coming from Fermilab now, that number is about 1 neutrino. So you have huge increases in the flux of neutrinos from having a local source here. Now, there's caveats on this. The neutrino energies are lower than the Fermilab. The cross sections are different. The physics reaches are a little different, but nonetheless, the event rate that you're going to get from these accelerator-based sources is enormous. So I want to spend a little bit of time talking about the cyclotrons themselves. There's as I say, we've been working for 15 years on these, and so they're very well developed. We have now money for building prototypes for the small one over here. And the large one, we've done a lot of studies, but there are existence proofs of these cyclotrons. There's one for the large one in Japan at a laboratory called RIKEN, which is very much the same technology as what we want to do. So these are not pie-in-the-sky accelerators. These are accelerators which are quite real. So I'd like to conclude by essentially saying there's compelling reasons for bringing these these accelerators underground. Now, there's another point, which is why SURF is the ideal place to do this. As you may gather, you may know, these cyclotrons produce a lot of neutrons and gamma rays, huge, they're messy. So I would never contemplate putting one of these machines inside one of the large existing caverns, which is close to a detector, because you need huge amounts of shielding then to protect this. But the wonderful thing about SURF is that there is so much space. That area where I showed as a potential place for putting these is in an area which can be isolated from all of the sensitive detectors. And having the capability of building this in an isolated spot is a huge, huge advantage. So the compelling reasons, huge increases in flux over anything else that you have. But the increases, one of the programs for these detectors are looking for environmental detectors, so geoneutrinos or solar neutrinos, which require very quiet backgrounds. So if we have a steady state cyclotron that is producing these things all the time, that's a background, you can't do the other things. On the other hand, if the flux rates are so high, we can run our cyclotrons at a very low duty factor, a few percent duty factor. So you still have maybe, and the Fermilab beam is on for just a few microseconds. So that there's very low duty factor there. But in the whole, you could still do the geoneutrino program with our cyclotrons. Because of the huge advantage of the huge flux rates, you can drop the duty factor down. And coming underground is, the background is so much better. The neutrino fluxes are cosmic ray fluxes are extremely low. And as I mentioned, the availability for isolating the cyclotrons from sensitive equipment. So the next step that we would propose is to host a workshop, and there's part, I learned about the setup series of theory experiments that are done here over the summer, and having this as a part of that program would be a lovely thing. And so an agenda could be, pick your source of neutrinos. So I've described two of them. There's another one. If you want a pure source of electron neutrinos, there's another accelerator reaction that you could do, which involves protons on aluminum. And the decay of sulfur-27 is a very good. So that's very, very much in the neutron, in the proton-rich side of the chart. But then, for your studies, whatever detector you want, whether it's Dune, whether it's Theia, whether it's also, some of the programs that I've talked to some of the theorists about, they really would like to be able to use the xenon, the dark matter detectors that are there too, because some of the effects that they can see are really based on those. So you pick your detector, pick whatever interaction you want, whether it's charge current or neutral current or coherent neutrino scattering or what we call BSM or beyond standard model. Then there's lots of opportunities to be explored there, to build a case then for doing this. Okay, with that, thank you very, very much. I would like to acknowledge some people, Janet Conrad particularly, who has been really a mentor for the last 15 years and has taught me all the neutrino. I'm an accelerator person. I didn't know anything about neutrinos when I started. So she's taught me everything I need to know about neutrinos. And Gabriel Orebigan, who's the Theia PI, and Jarrett for keeping me in the loop all these times, and I really appreciate that. And Stacy also and the SURF Institute for inviting me to come to do this. But the biggest acknowledgement that I really want to give is to the wonderful people that I met and worked with while I was working here and who have helped in the course of these adventures. So, thank you.
Well, thank you very much, Jose. You didn't disappoint on both fronts, or either front. The historical the overview was fabulous, and lots of ideas on future experiments that could possibly come to SURF. So we're happy to open it up for a couple questions here. Let's see. Let's look around the room. Any questions in the room to begin with? Here, let me get you the microphone here.
Do you find that there is collaboration between scientists at different detection sites for suggestions on how to create various experiments here? Or is it more like a competition where they don't want the success to be found here?
There's a tremendous amount of cooperation in all of these things. I mean, the resources that are necessary for building these detectors and mounting these experiments are very, very large. Initially, there may be some competition, but at a very high level, a decision is made, we're going to follow this path. And then everybody jumps on board. So there's opportunities for everybody that wants to work in the field to work. You have to be a little flexible in what you want to do. If you have a fixed idea, by God, I want to do that, and your idea isn't accepted, okay, then, but flexibility is the watchword, and is really the way in which things are done. You find collaborations for, well, you know, when I was working at CERN, before I started here, I worked on a large particle detector called Atlas. And when we were finished, there was a paper that was published on this. It had 3,000 authors. So, you know, large collaborations. In these fields, it's collaborations. This is for physics. Now, for the biology and geology, a lot of that is, you know, there's less expensive. Mostly, certainly compared with the dune caverns, you tend to have smaller groups. But thanks for the question.
Other questions in the room? It looks like we going once. All right. Well, we have one online here for Mike Ray. How does the neutrino source underground at SURF and the detectors planned here differ from data gathered at the near detector for Dune over at Fermilab?
Well, energy is lower, the spectrum is a little lower, but in many ways complementary. Yeah, it's just that we here there will be much larger detectors that were in place. So. And again, it would be the outcome of the workshops that would determine sort of really provide the detailed answer to those. But yeah, the near detector, the fluxes are very high, and the physics reach is also high. So it would be complementary.
Other questions? Oh, we have one here from Gabriel. Gabriel has a question about the samurai sword. Were you given one of the swords as a souvenir?
I wish. No, but it's a wonderful example of the of sort of, you know, of the teamwork and using capabilities that are there. I wish I would have. So I did ask whether or not they were still making the swords, or whether that was just a one-term project. And I believe the answer to that was a one-term thing, but there are other things that they're doing with the iron now also.
That's exactly true. All right, we're coming up to the top of the hour. Any last urgent questions? If not, let's thank Jose again for a fabulous talk.
Well, thank you for the opportunity to do this. It's been great fun. Thank you.
All right, I have a few announcements here to close us out. So once again, this talk is available online to view and share on YouTube, Vimeo, and at the Institute website, institute.surf/deeper-talks. Next month, you can join us again at the same time, same place for Under the Canadian Shield, Science Now, and the Future of Snow Lab with featured speaker Dr. Stephen Sukala. That will be on November 12th at 9 a.m. That will be virtual only. Your feedback, as always, helps improve the program, and we appreciate any suggestions you have for speakers or topics for future talks. Please fill out the short survey that you will receive immediately following the talk on Zoom and in your email. And with that, thank you again.